Okay, so we're going to take a look at question number 5 from the chapter 4 agenda questions. Let's run over here and see if we can get that. So they want us to solve the following system of equations. And what we're going to be doing here is something called the method of addition. So before we do this, I should try and explain what this method of addition is. In chapter 2, we solved equations using the method of substitution. But in this chapter, they want us to use this concept called the method of addition. And the method of addition, what happens is we're going to put, that didn't work, put one equation over the other. And then we add the two equations together, which sounds like a totally silly thing to do. And we are going to sort of manipulate the numbers so that one variable, x or y, disappears, which still sounds very mysterious. So let's do a few small examples before we even look at the questions that we're dealing with here. Let's do a few small examples of how this concept might work. So let's make up some numbers here. Let's say we had 2x plus 3y equals 18. And the other equation is negative 2x take away 8y equals 12. We're not really worried about anything else. But at this point, if we add these two equations, notice 2 and negative 2 disappear. So 3 and negative 8 becomes a negative 5y, and 18 and 16 becomes 30. But notice we only have one equation and one unknown. Once this has disappeared, we're only doing negative 5y equals 30, and we solve for y, and then we would put y back into the equation. So that's sort of one situation we could deal with. But let's say it was negative 2x plus 3y equals 18, and this was 4x take away 8y equals 12. So first off, let's get rid of that negative there. Now, if we add these two together, nothing is going to disappear. So what we would have to do is we would multiply this whole equation by 2, because we want the 2 to equal the 4. And we, of course, when we're adding them, we want one to be positive and one to be negative. So we'd have to go 4x, but we got to multiply the whole thing, plus 6y equals 36. And now we can ignore this equation. We're just adding these two. But now notice once again, the x disappears. And now we've got -8. So this is going to become a -2y, and 36, 46, 48. And we can still solve for y. So that's a situation where we only had to manipulate sort of one of the numbers. Now, let's find another situation where we have to manipulate all the numbers, or both equations. Let's see if we've got enough room over here to do this. Let's say we had 2x plus 3y equals 18, and 5y take away 8. Oh no, not 5y, sorry. 5x take away 8y equals 12. Now we can see that there's nothing we could multiply the 2 by to make it equal to 5, at least no whole number, and nothing we could multiply 3 by to make it equal to 8. So we need a common multiple. If we're eliminating the x, we need to go, the common multiple would be 10. So we'd multiply this equation by 5 and this one by 2. Oh, this one still has to be negative because something has to end up dropping out. So 5 times 2 is 10x plus 15y equals, I don't actually know what 5 times 18 is, 90. And down here, negative 10x. 2 times 8 is negative 16y. And 2 times 12 is 24. But again, now we've manipulated it. We've created a situation where the x disappears. This will become negative 1y equals 114. Again, we can solve for y. Now, in all of these cases, I've specifically worked toward eliminating the x, but you could specifically work toward eliminating the y and then solve for x. It doesn't really matter. So let's try and erase all this nonsense. And now we'll deal with the equations that we have up here. Maybe I need a bigger eraser, I don't know. Okay. So let's take a look at the equations they've given us. 6x plus 5y equals 9. And notice this equation is already in the standard form. The second equation, 4x take away 3y equals 25 is also in the standard form. So we're good to go. But we can see that there's nothing we can multiply the 4 by to make it equal to 6, or the 3 by to make it equal to 5. So we're going to have to multiply both of these equations by something. In this case, let's go for a common multiple of 12. So we want to multiply the 6 by 2, and we've got to multiply the 4 by 3, but we want one of these to be negative, so I'll make it negative 3. So now we're going to multiply through, so we get 12x plus 10y equals 18. And down here we get negative 12x plus 9y equals negative 75. And now when we add, our x disappears, so 0x. We've got 19, a positive 19y, and we've got 18 minus 75 equals a negative 57. And now instead of saying just solve by x, we actually have to do the solving, or solve for y. So y equals negative 56 over 19, or 57 over 19, equals, hopefully, negative 3. So once we know, or think we know this negative 3, and we're really happy it turns out to be a whole number, not that it has to be, but almost all of these equations they give us in the textbook, and I give you for exercises, will always work out to be whole numbers. It just makes life a little easier. Let's plug this 3 back in to these two equations and make sure it's equal. So 6x plus 5 times negative 3 equals 9. So we get 6x plus, well, take away 15 equals 9. So 6x equals 9 plus 15, which equals 24. So x equals 24 divided by 6, which is 4. So again, we're happy this is a whole number, but we're only really happy if when we put it in the other equation, 4x take away 3 times negative 3 equals 25. 4x plus 9 equals 25. 4x equals 25, take away 9, which is 16. So x equals 16 divided by 4, which equals 4. And so these two are now equal. So we're fairly sure we have the right answer. So when we want to look at our ordered number pair, which is what they mean by solving a linear system, our ordered number pair, x comma y, x is 4 and y is -3. And so what we mean by the idea that this thing solves this linear system is if we were to graph these two equations, the two lines would intersect at 4 and -3. Let's draw a straight line. So x, y, what we're saying is when x is 4, 1, 2, 3, 4, y is -3. Should be right there. Now, weirdly enough, at this point, and doing this method of addition, we don't have any idea where the actual lines went. So let's see if we can get an idea where they went. Let's take these equations and go over and try to solve them graphically. So if we were given these two equations and we're going to solve them graphically, what would we have to do? We'd have to (6x plus 5y equals 9), and we'd create this little strange symbol here. We'd go 0 and 0, and we'd plug in 0 into x, which would just give us 5y equals 9. Oops. Y equals 9/5. And what would that be as a decimal? 1.8. So 1.8. And we do the same for 6x equals 9 when we plug in 0 for y. So x equals 9/6. 9 divided by 6 is 1.5. So we've got two ordered number pairs. Let's take a look at the other equation. 4x take away 3y equals 25. Again, we're going to go x, y, 0, 0. And when we plug 0 in for x, all we're left with is -3y equals 25. So y equals 25 over -3. And what do we get there? A -8.3 repeating. And when we plug in 0 for y, we get 4x equals 25. So x equals 25 over 4, which is 6.25. So let's take these values I'll have to write them down so I don't forget them. So 0, 1.8, 1.5, and 0. Hopefully we didn't get any of the negative and positive screwed up. And then 0, negative 8.3, and 6.25, and 0. Let's go back to our diagram and try and graph them and see if they look like they cross at this point. So our first one, when x is 0, y is a positive 1.8. So this would be 1, 2, roughly right there. And when y is 0, x is 1.5, so roughly here. So we want to put a line that goes through those 2 points. And it looks like it vaguely could be going through the point that we need it to go through. Let's try the other one. When x is 0, y is at negative 8.3. So 1, 2, 3. Hopefully we left enough room to go to 8. 2, 3, 4, 5, 6, 7, 8, 9. Roughly like here. Negative 8.3. And when y was 0, x was equal to 6.25. So 4, 5, 6, 7, 6.25, roughly like right here. And again, we want to put a straight line through all those points. That one and that one. So we'd be very happy with our point that we came up with of 4, negative 3, because what they mean by solving a system of equations is find the one point that works for both equations. And when you solve this with the method of addition, you find the point. You don't necessarily, well, you absolutely do not find what the two lines look like. You only find the point where they cross. I only went through the whole process of solving them graphically so you could see that that's exactly what we're looking for, but we don't have to do the graph all the time. We just have to find the points. So let's try this all over again with the second set of equations. So I'll save this. We'll clear it all. And we'll try another one because they're so much fun. So let's look at the equations we have. Take away 7x equals 4y. So the first problem we see, this is not in the standard form. The 12 isn't in the right place, and the 4y is not in the right place. So we're going to manipulate this to be 7x. The 4y is going to leap over, become negative 4y. And the 12 will have to leap over, become negative 12. So that's okay. And the next equation, 6 take away 2y equals 3x. In this case, we have a similar problem. The 2y's in the right place, but the 6 and the 3x aren't. So the 3x will have to leap over, become negative 3x, take away 2y equals a negative 6. So now at least we have two equations in the standard form. Let's put one under the other. Negative 3x, take away 2y equals negative 6. So we can see we can't multiply 3 by anything to make it equal to 7, but we can multiply 2 to make it equal to 4. So we'll just multiply this bottom equation by a negative 2. The first equation can stay just as it is. Negative 7x take away 4y equals negative 12. But we're going to have to go negative 2 times negative 3. So it's a positive 6x. Negative 2 times negative 2 is a positive 4y. A negative 2 times negative 6 is going to become a positive 12. And did we make sure we got all the negatives and positives here right? What did we do here? That leaped over, and that has to be negative 6. Let's hope we're in good shape here. When we add this, negative 7 and positive 6 is going to become a negative 1x. The 4's cancel out, and this becomes 0. So if this becomes 0, then x must equal 0. So we'll work with that, and we'll put that in to both of these equations and see if that works. So what did we have? 12 take away 7 times 0 equals 4y. Well, 7 times 0 just disappears. So 12 equals 4y. Y must equal 12 over 4 equals 3. So that's good enough as far as it goes. Try the other one. 6 take away 2y equals 3 times 0. So 6 take away 2y equals 0. So 6 equals 2y. So y must equal 6 divided by 2 equals 3. So we're fairly happy. These two are equal. So our ordered number pair, x comma y, must be equal to 0 comma 3. In other words, when these two lines intersect, when x is 0, y is 3. They intersect at this point here. Again, unless we go to the extent of graphing it, we wouldn't know where the lines go. We just know the ordered number pair, where they intersect. And that's all we're being asked to do at this point. So let's call it quits there. And I'll try and save this nonsense. So we'll save a picture of it.